Here's a quick introduction to logarithms, which is going to be a pretty important topic. I want to start with an example based on money and compound interest. We know the formula for compound interest. Here's our master formula that we got. And I want to simplify it just a little bit. Let's go back a second and just say n equals 1. That means we're just compounding annually. And so we're going to have the amount at end of time t is the initial principal times 1 plus the interest rate to the t. Now there's various questions we can ask here. One would be given P, R, and T, find A of T. So that's just if I know the initial money, the known interest rate, and how much time, find how much money I have in the future. Okay, so that's predicting the future. More interesting is a question like given R, T, and A of T, how much money do I want to end up with in the future? Find P. And that's known as the present value problem. How much money do I have to have now to end up with a certain amount of money in the future? We can even have given A of T, how much money I want in the future, P, how much money I have now, and T, find the desired interest rate. That's a little trickier. It involves taking a root. Okay, but one problem where we got stuck, or where you can get stuck, is given A of T, how much money I want in the future, and how much money I have now, and a fixed interest rate, how long do I have to keep the money in there? Let's do an example of that. Let's say I want to end up with $2,000 from a starting of $1,000, and let's say the interest rate is 10%, so 1 plus r is 1.1. That's the equation I want to solve. Okay. So here, the weird thing is that the unknown is in the exponent. Now we've done a few kinds of exponential equations. Let me take those bullets away. Like, for example, 8 equals 2 to the x. That's not that hard to solve because it's very, very contrived. 3, the x is going to be, let's see, x is going to be 3 there, because we happen to know that 2 to the 3 is equal to 8. Okay, so in very, very special situations, we know that there's some simple answer here. Or we could have like 10,000 equals 10 to the x. Well, we then know that x is going to be 4, because we happen to recognize that as a power. But we don't have that situation here. We can do a tiny bit here, which is divide by 1,000 and focus, in other words, on the growth factor. We want the growth factor that multiplies our original investment to be 2. This is a very standard problem. It's called finding the doubling time for investment. How long is it going to take for my investment to double? The 1,000 and 2,000 aren't super important. It's really about doubling. But we don't necessarily know how to find that t. Okay? We're not going to actually, I'm not going to show you some magical method of finding it. I'm going to show you first here in this video just a method of naming it and talking about it. And then we're going to go, it's going to split from there. It's going to be either kind of calculator calculations. Once we've named it, we'll be able to find it on the calculator. And then we're going to see some very cool properties of this operation that we've invented and named. Okay, so we'll come back to that problem in a second. Let's just do, let's just rewrite these in a little bit of a different way. Okay, so let me just go ahead and go back to this. 8 equals 2 to the x. I want to give a name for this operation of solving for the exponent. And so what it goes by is it's called the logarithm. Let me just write it out and then explain it. Actually, let's say, okay, yeah. So here, if I'm solving 8 equals 2 to the x, then the name for, I'm playing the mystery exponent game. The name for the mystery exponent I have to raise the base 2 to in order to get 8 is called the logarithm to the base 2 of 8. So it's the answer to the mystery exponent game. So logarithm is our name for the answer to the mystery exponent problem with a fixed known base. Here, the base was not the mystery, it was 2, and the 2 base here shows up in this subscript here. So this is pronounced as the logarithm to the base 2 of 8, or log 2 of 8. So similarly, if I say that, if I look at 10,000, that's known to be 10 to the 4th. Another way to say that is if I take the logarithm to the base 10 of 10,000 that says, is there some number I know that when you raise 10 to that power I get 10,000? Yes, the answer is 4. In general, here's the statement. Let's put in letters everywhere. If I know that y is some base b to the x, then that is equivalent to saying that the logarithm to the base b of y is equal to x. So here you want to think usually as b is a known fixed quantity and y is known, and I want to figure out x. And this is our name for the answer to that question. In some very limited cases, we can actually do that by hand. Log base 10 of 10,000, log base 2 of 8. This is of course equal to 3, for example. But usually we aren't able to do that. Okay. On the calculator, you'll see a button just called log, and log of y is an abbreviation because we use the base 10 number system. It's abbreviation for log 10 of y. Okay. And so we're sort of programmed by having 10 fingers to think of this as being special. You'll also see something called ln. That is the log to the base e. That, remember, that e is special because, for example, we found it in the continuous compounding problem. There's many other reasons why e is special. Let me put that down. Many other reasons. But we know that it came in the continuous compounding problem. And so we're going to be using this this stands for natural log, log naturel in French. So these are the two buttons we have on the calculator. Now, unfortunately, we still don't know how to solve this problem. Because what this would be t would be the log to the base 1.1 of 2. And there's not a calculator button that gives us the log to the base 1.1. We just have log base 10 and log base e. And so what we need, and we won't do it in this video, what we need is to understand logs better. It turns out that there's some very cool properties of logs, and that will be the key to solving this problem. Let me say one more thing about logs, though. Another way to express this is, suppose we look at the function 2 to the x and graph that. So let's look at, for example, this graph says that the 2 to the third power is right about here, which is in fact 8. And 2 to the 2 is here, which is 4. And the problem that we're asking with, for example, here, is to go backwards. I look at the value 8 for the y, and I say, does that intersect something nice here with 3? Okay. 4 would give me 2. So instead of going from the x's to the y's, I'm going from the y's to the x's. That should give you a hint that what we're doing here is inverse functions. We're just defining the log, or to be explicit, log base b, to be the inverse function of the function f of x equals b to the x, the exponential with that same base. And so that's going to help us graph it. It's going to help us understand a lot of things about the logarithm function. There's much more to say, but that's a good intro.